In order to figure out how to factor trinomials whose leading coefficient is not equal to 1, let's start as we did before by multiplying a couple of binomials that will end up with a trinomial whose coefficient is not equal to 1, and then see if we can reverse the process. Okay? So foiling, we have 2x squared plus 2x minus 5x minus 5. Combining like terms, we have 2x squared minus 3x minus 5. Okay? So that will give us a polynomial, trinomial, with leading coefficient other than 1. And we can't turn it into a 1 by factoring out a GCF, because this 2 is not in common to all terms. So how, if we began with this polynomial, how would we arrive back at the factorization? Well, the key is this step. Because if we can take this trinomial and split it up, or split the middle term up, so that it is now 4-term polynomial, we can finish it with grouping. Watch. 2x squared plus 2x minus 5x minus 5. If we group that thing, we'll turn this into a plus a negative 5x. What's going to happen? Well, here we'll factor out a 2x. The remaining factor will be x plus 1. Here we'll factor out a negative 5. The remaining factor will again be x plus 1. And so we can factor that x plus 1 out. And the remaining factor is 2x minus 5, which is exactly what we started with. So there are going to be 2 steps to this process. The first step is to split the middle term up into 2 terms, and the second step will be to take that 4-term polynomial and factor it by grouping. So we need to figure out how to split this up. Can we split it up any old way? If we try a different combination that makes a negative 3, then it's not going to work out necessarily. So we need a method that will work for us every time. And there is such a method, which is sometimes called the AC method. And here's why it's called the AC method. These polynomials we're working with generically look like ax squared plus bx plus c. Before we looked at polynomials where this a was a 1. Now we're letting it be anything. So this is where the name AC comes from, because we need to look at AC. Okay? In other words, a times c, the leading coefficient multiplied by the constant. From there, it's very similar to factoring a trinomial with leading coefficient 1, because we're going to be looking for pairs of numbers whose product is AC. Okay? And, of course, like before, we want the sum to be B. So the only difference is instead of looking at C, we're looking at AC. And then when we get the correct pair, we're going to use it to split this term instead of immediately being able to write the factorization. See, in this example, AC is 2 times negative 5. negative 10. So, similar to before, we can look for pairs whose product is negative 10. We want the sum to be the middle coefficient, negative 3 in this case. So since it's negative, we want the larger of our factors to be negative, which means the smaller factor will be positive. So I'll start with a positive 1. So our first pair is 1 and negative 10. The sum is negative 9, not negative 3. So we continue on. 2 and negative 5. The sum is negative 3. That tells us this is the pair we want. And so those are the numbers that we use to split up our negative 3x. Since negative 3 is equal to 2 plus a negative 5, a negative 3x is going to be equal to a 2x plus a negative 5x, or 2x minus 5x. So that is how we're going to be able to split up the middle term. That's the AC method. And then we'll be able to proceed by grouping now that we have 4 terms, and that'll finish the factoring for us. Let's see another example. We want to factor 8r squared plus 14r plus 3. Again, we cannot take out a GCF to get rid of that 8. So what do? We find AC. 8 times 3 equals 24. We want to find a pair of numbers whose product is 24. And when we get the pair that adds up to 12, or up to 14, we'll be done. Okay, so 1 and 24. The sum is 25, not 14. So we'll go to the next one. 2 and 12. There it is. And if it hadn't been, we could have continued on to 3 and 4 and so on until we got the one that worked out correctly. So, this is the correct pair. That means we're going to take our 14r and split it into 2r plus 12r. We're still going to have our 8r squared and our 3. So by the AC method, we have split the middle term into 2 terms. We now have 4 terms, and we can apply the grouping method to finish. Here, there is a 2r in common. The remaining factor will be 4r plus 1. Here, there is a 3 in common. Again, the remaining factor is 4r plus 1. And the AC method is designed precisely so that it will give us the exact 2 numbers to cause this grouping to work out. So this binomial factor will be the same every time. If you get 2 different binomial factors, then you can be sure you have not gotten the correct 2 numbers here in your split. Either that or you've factored incorrectly as you were trying to do grouping. So since we got 4r plus 1 in common, we'll factor that out. The remaining factor is 2r plus 3. And if we were to check that by FOIL, 8r squared plus 12r plus 2r plus 3, combining like terms, we are going to get exactly the polynomial we started with. So that confirms that this is the correct factorization. This will also work if we have additional variables. 10n squared minus 13np plus 4p squared. In this case, we just know that we're going to end up with something of the form number times n plus or minus a number times p for both of our binomials. Okay? Because when we take the middle terms, n times p, that's exactly what the variables of our middle term are. So we proceed exactly by the AC method so that we can get 4 terms, and then finish by grouping. 10 times 4 gives us 40. We want pairs of numbers that make 40, and when they add together, they make negative 13. Well, 40 is positive, and negative 13 is negative, so we need 2 negative numbers. All right, so negative 1 and negative 40. Start at the beginning. Their sum is negative 41, not negative 13, so we continue. Negative 2 and negative 20 makes negative 22. Negative 3 doesn't go into 40. Negative 4 does. Negative 4 and negative 10 makes negative 14. Almost there, not quite. Negative 5, negative 8. Their sum makes negative 13. So this is the pair we want. We will split negative 13 into negative 5 minus 8. Of course, we got to remember our NP. And there's our polynomial. We factor by grouping. Here, in the first 2 terms, there is a 5n in common, leaving a 2n minus p. In the second 2, we'll take out a negative 4p, leaving 2n minus p again. 2n minus p in common, we factor it out, leaving 5n minus 4p. One last example. We want to factor 21x squared plus 14x minus 56. Notice that in this example we can take out a GCF. 7 is in common. Okay. It will not get our leading coefficient to be a 1, but it will reduce our numbers so that we work with smaller numbers as we work out the AC method. 3 times negative 8 gives us negative 24. Okay? So we need 1 positive and 1 negative factor to add up to, to add up to 2, okay, which is positive. So negative 1 and 24 will make 23. Negative 2 and 12 will make 10. Negative 3 and 8 will make 5. Negative 4 and 6 will make 2. 2 is what we want. Okay? So it's the negative 4 and 6 that will work for us. We get 3x squared minus 4x plus 6x minus 8. Continuing on, there is an x in common here, leaving 3x minus 4. There is a 2 in common here, again leaving 3x minus 4. We factor out the 3x minus 4 all along the way, keeping our 7. We have an x plus 2 left as our remaining factor. If we had not taken the 7 out, then our AC would have been 21 times a negative 56 equals negative 1176. We would have had much bigger numbers to work with, but we still could have done it in the end. We just would have had a 7 to factor out of one of our binomial factors. This is what it would have looked like in that case. The pair we need is negative 28 and 42 because that would add up to 14. We split, group, we factor, we end up with 7x plus 14 times 3x minus 4. But there is a 7 in common here that we can factor out, leaving x plus 2. And so we get 7 times x plus 2 times 3x minus 4, exactly as before, only with bigger numbers and therefore more difficult work.